Alrighty guys, here we got section 2.2, the limit of a function. So this is our first formal introduction to the concept of a limit. I mentioned it a little bit in the previous section. Okay, so what do we mean by a limit? So first of all, let's describe what we've got over here. So if you did the pre-lecture, hopefully you saw a graph that looked a lot like this. I kind of made this one up, made up the numbers myself, but it captures, I think it was the last problem from that pre-lecture. So what we've got here is we've got one function, all right, but it's got two pieces. So I don't have a rule for the function. So f of x over here, this function, call it f. If I labeled it over here, I would call it f of x to indicate that what the rule is with respect to the variable x. But I don't really have that rule, okay? If I did, this might be one of the ones that you saw from some of those chapter 1 homeworks. This might be a piecewise function, okay? So I'm not going to attempt to create a formula for this, but what you might see is you might see some kind of rule filled in for all these x values, right? And this looks like maybe x values coming from the left up to, and not including 1, right? Because at 1, the function jumps up here, but I might have, this might say if x is less than 1, right? And I might have some rule. Maybe it looks like the bottom of some kind of parabola. And then if x is greater than or equal to 1, meaning when it's equal to 1, looks like the function lives up here with that closed dot as opposed to our open dot. And then as x gets greater than 1, as x moves to the right, as the function moves to the right, it's still defined for over here. So, and we might have some kind of rule. All right. There's a couple other things going on here, right? I've got a little hole right there. So if I was trying to create a rule for this one, we'd have to think about how exactly to define that if x had to be less than 2. But anyway, just trying to, the emphasis of what I'm saying here is that even though I've got two pieces to this thing, it's really one function. So I called it f. It is possible sometimes you'll see different functions on the same plane, f and g, or you might call them different things. But this is what we got right here already. Also, just a note while I'm on this topic, in the past I've had students kind of see a discrepancy between here when you define functions with a rule, calling it f of x, right? Again, really the name of the function is just this letter out here, f. So if I say, what's the name of this function? It's just that letter f, but then that's not something different than if you write it as f of x. They kind of mean the same thing, but oftentimes we might just say the letter. Anyway, back to the concept of limits, okay? So we've got this one function here, graphed in the plane. I labeled my x-axis in green, so just a couple coordinates, 1, 2, 3, and our y-axis up here in the blue. Let me call that y. And then I've got this function f, okay? So before we jump into limits, let's just go over some function notation. So again, we could have a function, and remember, f of x would be the general rule for the function. So that would have x featured in the formula, let's say. I use the term rule, but some people say formula. However, if you see something like this, let's say f of 1, right? We read that as f of 1. That means what's the y value when x is 1, right? What's the function value or the y value of the function when x is 1? And so here, without having an explicit formula, we can still just read this from the graph. So when x is 1, I jump up to this dot. It looks like it's around that height of 6. That's what I was aiming at. And so I would say f of 1 is equal to 6. Okay. Is it also fair to say that f of 1 is equal to 2? Right? Because the function looks like it's heading towards that value of 2 right there. But we use, in math, we use these open dots. That's kind of a void or a gap. So in this case, I might say it's a gap. So these two ends are coming there but not really meeting there. Here, it's just kind of stopping a little bit shy of the actual value 1. Right? So it would not be correct to write f of 1, let's say f of 1 is not equal to 2, even though I've got that open dot right there, okay? What if I said f of 2? So over here, if I look to this x value 2, f of 2, I don't even want to write an equal sign. I'm going to write, I'll use this phrase DNE to mean does not exist, okay? Or is undefined, sometimes you'll say. But yeah, so anyway, so I've got this curve right there. Clean that guy up a little bit. And so that's the idea. So we can speak about function values. What do we mean by a limit? Okay, so let's choose a point. I'm actually going to choose this point right here where I don't really have an x-coordinate labeled. But if I drop down, and put a little tick mark right there. I would say that looks like about 1/2, right? If there's 0 and 1. Some folks like decimals. When you're doing a lot of stuff on WebAssign, my other computer's there, so when you see me pointing there, that's what I'm looking at. When you're doing stuff on WebAssign, you might often use a lot of decimals, right? Especially if you're crunching things with calculators, entering values in tables, you might like decimals. I like fractions, so I'm going to call this 1/2, 1/2 right there. So there we go. So if I wrote what is f of 1/2, then let's use the graph again. So I'm come over to my x-coordinate of 1/2, jump up to the graph. Looks like it's the height of 1, right? So we could say f of 1/2 is equal to 1. Okay, what if I want to talk about the limit? So if I'm talking about the limit, and so I'm going to introduce, limit comes along with its own notation. I'm going to write this, lim, so lim, and then underneath there as x. So since x is we call this the independent variable, right? The one that we're choosing to plug into a function. The limit as x approaches the value of 1/2. Okay, so that's kind of how you read this arrow right here pointing to the 1/2. Means as not if I plug 1/2 into the function, right? I know if I plug 1/2 in, I just get 1, right? But as x approaches 1/2 of this function, and here I'm going to write f of x, so you would typically include the x right there. In other words, as this x value approaches 1/2, where's f of x going? Where's the function going? Okay? So, a couple sections down the line in this chapter, we're going to define continuity in terms of limits. So probably a way you haven't seen it before. But I think most students have a intuition of what continuity means, right? So sometimes people say a continuous graph is one that you can draw without lifting your pencil or without lifting your marker or something like that. And we think about continuity at a point, right? In other words, this piece of the graph, I didn't have to lift my pen to draw. So this little piece is continuous unto itself. This piece seems like I can draw, right, without lifting my pen. But then because of that circle, you kind of have to stop this piece and then start on the other side. So you kind of got to lift your pen to draw this. So overall, I would say this function is not continuous, or you could say it's discontinuous at a few points. But at this point, it's continuous, right? I can draw the nice smooth curve straight through there, okay? So if I said the limit as x approaches 1/2, what I'm thinking is not what point I'm at or what height I'm at, but where I'm going. Right? So if you approach from this side, these values are larger than 1/2, right? Here I'm at a height of 2, and then maybe like 1/2, and then I'm creeping down towards the height of 1 as I approach from that side. And if I approach from the right, and I creep down, again, this looks like it's starting at 2 near that open hole, and it's decreasing around 1.5, and then right there it's approaching the height of 1. And so it's fair to say, using this language, that the limit as x approaches this value of 1/2 of the function f is equal to 1. Okay? Notice in this case, because we're continuous there, it's kind of going backwards actually, but because, so the graph looks continuous there, the function value was 1, and the limit is 1, right? So where is it going? It's going to where it is, right? That makes sense. When we finally discuss continuity, we're going to define it in terms of limits, and we can't say that these things equal each other because the graph is continuous. At that point, we're going to be proving that it's continuous at this point by showing that these two things are equal. In other words, that the function value matches the limit. Okay? But that's down the line. So anyway, here we've got function values, which will say f of the x value is equal to 1. Okay? Then we've got this limit notation. And again, so this means the limit of the function f, or of the function f of x. So I'm not putting the x value in there. I'm leaving it written as an x. But down here, we're telling the student or telling the reader where x is going. X is trending. As x trends towards 1/2, the y values trend towards 1. There we go. We've got a limit. Okay? Perfect. Notice I discussed now when we were approaching from the left and the right, and we wanted those things to agree. Okay? So let's move on. So that's our first example. Let's look at this thing right there. So I said earlier, if I want to write f of 1, f of 1 means where does the actual function live? And so remember, these two pieces of the graph are one function, and there was something hopefully you've heard in the past, the vertical line test. If you draw a vertical line through a function, it should only be touching the function at one point. It can't touch it more than one. And so the vertical line going through this spot where x is 1, it's not touching the graph there because that's an open dot, but it is touching the graph up here. So we said earlier f of 1 is equal to 6. cool. All right, what can I write this though? So let's say, what's the limit as x approaches 1 of my function f, or of my function f of x, okay? I'll put an equal sign for now. So let's think about this. So the function value is 6. Let's think about how we're approaching there. So as I approach, we say from the left, meaning x values that are to the left or slightly less than this x value. So from the left, sometimes I'll trace along the x-axis, but really what I'm doing is tracing the graph. As we move towards the x value of 1, where's this piece of the graph trending towards? It's going up towards the height of 2, right? Going up towards the height of 2. But what about this part? As we come from the right, or from x values slightly greater than 1, then we're climbing up towards that height of 6, okay? So in that case, as we approach from the left and the right, we're not going to the same place, we're going to different values. I usually erase the equal sign in that case, and I'm going to use my D and E. Does not exist, okay? In other words, that limit doesn't exist. And so I'll use kind of a metaphor in a second to hopefully try to explain that a little bit, but that's what we've got so far. Okay, so the limit doesn't exist. Let me put that in a box so it's a little bit clearer to see. However, what if I write this? So I talked about the limit as x approaches 1 from the left. There's notation for that, and that's going to be this. If I write this, lim x approaches 1, and then we call it a superscript, almost lives where an exponent would live. I'm going to put a little minus sign. Okay, this means the limit as x approaches 1 from the left. Okay, that's what that means. Just write left right here. One way to interpret that is 1 minus a little bit, right? If you're approaching from the left of 1, then maybe you're like 0.9, which would be 1 minus a tenth or something like that. So it's 1 minus a small quantity. The limit as x approaches 1 from the left of this function, that exists, right? To me, that exists. In other words, where is this function trending towards? It's trending towards the height of, I'm looking at this piece because I'm traveling along the piece from the left, going to that height of 2. So the limit as x approaches 1 from the left of this function is 2, okay? Even though the function doesn't actually live at 2, the function takes a jump right there, but as we approach from the left, that's where we're trending towards. All right, so we've got that, our left-hand limit, we might call that, and then we can speak of a right-hand limit. So underneath that, let me write lim as x approaches 1 from the right, and we use a plus sign, right? Notice this 1 with the minus, that doesn't mean -1. So sometimes you might see a negative out front, but that means from the left. Here we've got from the right. And our function is still called f. So the limit as x approaches 1 from the right of this function is, if I follow from this direction and head up, we're going to that height of 6. All right, and there we go. So we've got what we can call a left-hand limit. So I could say the left-hand limit here exists, and the left-hand limit is 2. The right-hand limit exists and is equal to 6, but these are two different numbers. So I call this sometimes just the overall limit. Technically, this is just called the limit, but I call it the overall limit, kind of taking both of these into account. Doesn't exist. All right. The analogy I kind of use to describe that, and maybe some more familiar terms, is let's say left-hand limit is your mother and right-hand limit is your father. Okay, so let's say it's 5 p.m. They're both coming home from work. So your mom's coming home. She's on her way home from work, and your father's coming home from work, right? So if the two people are going to the same place, if somebody asks you where are your parents going, you'd say they're going home, right? They're both going to the same place. So I can use the overall term parents to describe the behavior since they're doing the same thing. Okay. On the other hand, though, since these values are different, if your mother is going to the grocery store and your father is going to the hardware store, and somebody says, "Where are your parents going?" there's no answer to that question, right? You'd have to describe each separately, but you can't say overall where your parents are going. That's exactly how the idea of a limit works. So the left-hand limit might exist, might be going somewhere. The right-hand limit might exist, but if they're not going to the same place, then it doesn't make sense to talk about sort of the overall limit, or just this limit in general. Okay, so there's a couple of examples. So here we looked at a spot where the function existed at that height. The left and right-hand limits were the same, so the limits existed. And ultimately, like I mentioned in the future, we'll use that to prove that the function's actually continuous right there. just using our layman definition of continuity or continuousness, if I said is the function continuous when x is 1, it's pretty obvious that it's not, right? Because it's broken right there. You can't get from here to here without lifting up your pen or pencil, so not continuous at that point. All right. Okay, so we've seen a spot where the function exists, the limit exists, and they're both the same. That's a possibility. We've seen another spot over here where the function exists, but the limit does not exist, right? However, the left and right hand limits exist. So, got different ways that we can sort of combine all these ideas. So let's move down the line, move down our x-axis, if you will, and look at another spot. So what about this thing, 2? So now, what if I write f of 2? And I think I said this earlier, right? Earlier as an example. If I look when x is 2, the function, that open dot means the function doesn't exist. This piece exists for values less than 2, and this piece exists, but at 2, the function doesn't exist. Just takes a little gap, took a vacation. So f of 2, and I'm always reluctant to keep an equal sign, because it doesn't really make sense to say f of 2 equals does not exist, right? It's just f of x does not exist, right? So there we go. So in this case, I'm sorry, f of 2 does not exist. Okay. What about the limit? So let me do this one. I'll do the 2 pieces first. So let me write the limit as x approaches 2 of f of x from the left, and the limit as x approaches 2 from the right. Okay? So we'll set them both up. So here, the function does not exist at that spot. But as I approach from the left, where's it go? It's trending towards that spot, right? Which looks like it's at the height of 5. So as I approach from the left, the function's climbing to a height of 5. All right, so let me put that in. As I approach from the right, the function is sort of descending to a height of 5, right? So the limit as I approach that x value of 2 from the right is also 5. Therefore, you might have seen these little triple dots in a science class sort of to mean, therefore, the overall limit here exists. The limit as x approaches 2 without one of those little superscripts. So just in general, as x goes to 2, the function is going to 5, right? It's kind of, these 2 positions are sort of meeting right there at that height of 5. So the limit as x approaches 2 of f, or of f of x, is equal to 5, and there we go. Alrighty. So if you're thinking back through the other cases that we've seen, this is a new scenario now. Now the limit exists, but the function itself does not exist. Okay, that's interesting, and we'll see lots of examples of that. That's important. So there we go. So we can have them all match up. We can have the function existing, but the limit not existing. We can have the limit existing here, but the function not existing. And yeah, that's about it as far as the different combinations of these cases. But we'll look at a few more points along the line, or along this curve f here. All right. What if I wrote this? I could do this 2 different ways. I could say f of 0, and then I can also, or 2 different things I'm doing here. The limit as x approaches 0 of my function. Okay. Why am I choosing 0? Well, first of all, whenever x is 0, that's your y-intercept, right? So that's just worth reiterating. The reason I just want to point this out is I had something very similar to this in a past semester on paper that I passed out, and somebody told me that these 2 things don't exist because there's no point there. And I can see why they said that, but that's sort of a misconception about what a point is, what a line or a curve is in this plane, and so forth. So I think what that student meant is I didn't draw a big dot right there, right? But I could. And if you watched my previous video, I emphasized that the dots are kind of a little bit inaccurate. We do that visually so we can see clearly that that's the point that we're interested in. But yeah, this point is crossing the axis right there. Right? I mean, so I can add the dot. So that point does exist. And then from there, you know, we can argue what that looks like. To me, I'll say that's 1.5 or 3/2. And then as I approach from the left and the right, it's going to that spot, right? There's no funny business happening with gaps or anything like that. So the limit as x approaches 0 of f of x is also 3/2. Okay? No big deal. But just wanted to kind of get that out there. The last point I want to talk about is this thing, because sometimes in math we'll talk about the end behavior of a graph. In other words, what's happening to these functions as they keep going. So let's say this piece, maybe I continue this piece like this, and sometimes you might see a little arrow like that pointing in some direction. You can take that to mean that in this case it's pointing up, but you can take that to mean that it's existing for all these x values moving to the left. In other words, as I keep moving to the left, it's just going to kind of go in that direction up really high. Sometimes you see things defined on sort of what we call a closed interval, though. So let's say I just have an end point right here without the arrow. If I was talking about the domain of this function, then you might say that the domain ends at the x value 3, right? In other words, the graph doesn't exist beyond there, so the function doesn't really exist there. So can I talk about the limit at that spot? And so if I wanted to say the limit as x approaches 3, of my function. Well, first of all, let's locate the height of that point. There's a point there. The function's defined there. So f of 3 is equal to 6. We could write that. But the limit as x approaches 3 should also be 6. The little caveat is, since it's not defined, f is not defined here for x values to the right, then we should include the little minus sign here, right? That little from the left indicator, because this is not truly accurate since the function doesn't exist. You can't talk about both sides. But there we go. Put that, and now that's perfectly accurate. All right. Okay, cool. So we've got our basic definition. Let me do erase this and do another couple of examples. Or should I stop this video and start a second one? I think I'll do that since we're about 20 minutes in. So I will pick up for part 2.